last lecture had some pretty heavy formalism so that we could get to the point of doing diagrammatic perturbation theory. In this lecture, we're going to see why did we go to all that trouble. Okay? We're going to see what can we use this for to learn about the physics of a system. Okay? And since this is sort of our first inroad into interactions, we'll see a bit about what this does, and in particular, how it affects the pressure in a real gas as opposed to an ideal gas. Before we look at how to use the diagrams to get some physics, I just want to take a little bit of time to talk about symmetry factors a bit more. There's been some discussion on Piazza about this, and I had intended to give you a bit more anyway. So the key thing to know, in fact, some of the discussion in Piazza was about group theory, and people were wanting to use like results from the theory of finite groups. There's only one thing you really need to know that kind of comes out of group theory, and that's that the symmetries of a planar figure can be boiled down to rotations and reflections. Okay? And in particular, some number of rotations and either one reflection or no reflections. Okay? So that's one important thing to know, is that you don't need to think about multiple axes of reflection, because if you can find multiple axes where it's symmetric on reflection, those axes should somehow connect through the rotations of the figure. Okay. Great, so let's look at a few examples. First one here, we've got a pentagon. Okay, 5 particles, 5 Fs, and this pentagon is symmetric under rotations. 5 rotations, right? I can either not rotate it, I can rotate it by 72 degrees, 144, right? Or in radians, because we're not animals. In radians, 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5. And if you went to 10, that would divide and give you 2 pi, you're back to your 0, right? So basically a rotation that just takes one point to the next point. This has also got an axis of reflection symmetry, right? So, but I said you only need to know whether or not there is a single axis of reflection symmetry. So this is a yes-no question. And in this case, the answer is yes. Now you could look at this thing and say, well, wait a second. That reflection axis isn't any better than this reflection axis or this reflection axis. And that's true. They're all equally good because they're all connected via rotation, right? So if what I wanted to do to this figure is reflect it and then rotate it, okay, I can do that. If what I wanted to do is, say, reflect it over this axis, right, what I can do is rotate until this point is up here, then I reflect, then I rotate back down. Okay, so by composing rotations with a single reflection, you can make all of the symmetries of the figure. Okay, so in this case, we've got 5 rotations. Yes, we have a reflection, so 5 rotations and 2 reflections, right? Either we do or we don't reflect. This is just like here with the 5 rotations, right? Do you think rotating 0 is a rotation? Well, it is. It's the non-rotation, right? So if we had a figure that was completely asymmetric, had no symmetries at all, you would say, well, I've only got 1 rotation and there's no reflection, so I'd have 1 times 1 equals 1. Okay, that's sort of your check that this makes sense. So for the pentagon, the symmetry factor is 5 times 2, it's 10. Okay, good. Let's look at another one. This is, I annotated this so much you can't hardly tell what it is anymore. Okay, here's the clean version of it. So it's a square with a connection along one diagonal. Okay, so this is a figure with 4 points, 4 particles, but 5 Fs. Okay, so this has 2 rotations, right? Either 0, don't rotate it at all, or rotate it fully by pi, right? So all the way around, because this diagonal has to be on itself again to be a symmetry. Right? And then I drew this red reflection axis. Said this is our reflection axis, right? And so It's got 2 rotations, 2 reflections. Symmetry factor is going to be 2 times 2 equals 4. And since this is maybe a less trivial case of you don't need to draw 2 reflection axes, I just wanted to go through it because this is also a reflection axis, right? If I reflect along the diagonal, the drawn diagonal, that will reflect, right? That's still symmetric. The diagonal is still in the same spot. You still got your square. And this reflection axis is not a pi rotation away from this one, right? These are separated by pi over 2. So you might draw both of them and think, I don't know. He said I could do it all with 1 reflection and rotations, but it doesn't look like it. So you can, and I actually drew it out just to be clear. So if I reflect along the red axis, right, what I call the reflection axis, then all I'm going to do is swap 2 and 3, right? So this becomes 1, 3, 4, 2 instead of 1, 2, 3, 4. Okay. Now I'm going to rotate by pi. So 4 comes around to where the 1 was, 2 comes around to where the 3 was, right? 1 to 4, and 2 up to where the 3 was. So now we've got our figure. If instead I wanted to reflect across the blue axis, well, the 2 and the 3 aren't changing. 1 and 4 swap spots. It's the same thing. So even though it's not obvious because these 2 reflection axes are not separated, or rather are not connected to one another by one of the rotations in your rotation set, it turns out you can still write the whole thing as a single reflection plus all of your rotations. So in this case, we've got, as I said before, 2 rotations and a reflection axis, which means 2 options for reflection, either do it or don't. So a total of 4 symmetries. Okay, that's the symmetry factor. Keep going. If I take a pentagon and give it an extra side, so 5 particles but 6 Fs, there is no rotation symmetry anymore, right? There's no way that you can rotate this thing that makes it look the same again. But it does have a reflection, it has a single reflection axis. Okay? If you try to reflect it anywhere else, you're going to do something funny to this diagonal. But if your symmetry axis cuts perpendicular to the diagonal, then when you reflect, you're good. So this one actually has only 1 rotation, which is to say, don't rotate it. So 1. It does have a reflection, so 2, so the symmetry factor is 2. And then one last one that I realized could trip you up. If I draw this diagram as a T, it doesn't have any rotation symmetries. It just has 1 reflection, right? I can reflect it, but that's it. The thing is, that would suggest 1 times 2 is 2, and that's wrong. So when you're drawing the diagrams and you want to figure out their symmetry factors, do be a bit careful. You need to sort of draw it in the most symmetric looking way possible so that you get the correct symmetries. So in this case, don't draw it as a T, because that's weird. That's like squished down. The most symmetric way to draw this looks like a triangle, right, with a point at the center. And now you can see clearly I have 3 rotations, right? This is like just like the triangle that we looked at before. Hands can't do a 360 or a 2 pi. But you see it's got the same symmetries as an equilateral triangle, right? It's got 3 rotations and it's got a reflection axis. 3 times 2, this has a symmetry factor of 6. Okay. So I hope that helps you get a better feel for symmetry factors, and we'll make you a little more confident on the problem set. In the last lecture, we saw how we can write this configuration function in terms of diagrams. And we came upon the configuration function because we sort of started by asking what happens when we add interactions to our ideal gas. And along the way, we found that the partition function could be factored into the ideal gas part and then sort of everything else that was left over. So we had an ideal gas partition function in front of all of our diagram terms. And so we could factor that out and leave behind this configuration function. So the configuration function is essentially the difference between our real interacting gas and the ideal gas. Now, partition functions are great. In principle, you can calculate everything from them. One of the more physical things we can calculate from it is the Helmholtz free energy. And the free energy has this really simple form. It's just minus kT times the log of the partition function. And since our partition function is already written as a product, when we take the log, that'll separate out into two terms. First term is just minus kT log of the ideal gas partition function. This is going to contain all the stuff that we sort of already knew. And now the second term, the difference between the real gas and the ideal gas, is this minus kT times the log of Z sub C. Okay. So our configuration function controls all the interaction parts. And now something that I told you in the last lecture is going to come in very handy. I told you this. I definitely didn't prove it because that's way beyond the scope of this course. So you're just going to have to trust me on this part. But the configuration function can be written as the exponential of the sum of all of the connected diagrams that stay connected when you remove any dot. Okay. So I call these the one dot irreducible diagrams. So I cannot remove a single dot and cause this to become a disconnected diagram. Okay. So if I can write the configuration function as this exponential of a sum of a specific set of diagrams, taking the log just peels away this exponential bit. So we've got the Helmholtz free energy again is minus n kT times the log of 1 over the phase space density. So if you remember, the partition function for an ideal gas is just 1 over the phase space density for a single particle. And then when you've got a gas of n particles, it's that raised to the n. The n pulls out of the log, right? And hopefully you now recognize this as 1 over the phase space density, right? So we've got our number divided by the volume in physical space and divided by the volume in momentum space. So altogether, this is 1 over the phase space density. Great. So this is the ideal gas bit that we already understand. Then what's left, when we take the log, it cancels off the exponential here. So we just have minus kT times our sum of this special class of diagrams. Okay. Now, you don't normally go around with your Helmholtz free energyometer, right? So something that's physical that we can measure straightforwardly would be pressure. So let me not leave this at the bottom of the screen. Okay. So the pressure is minus the derivative of the Helmholtz free energy with respect to volume, right? Something you saw in 358. We've used it earlier in this course as well. And because it's the Helmholtz free energy, we picked that because it's going to be a derivative with constant n and t. And we have written this already in terms of n and t. So this is just the thing we want to calculate pressure. And you will not be surprised by the result when you do this to the first term. Because this is the ideal gas term, we get nkt over v, just as you would expect. Okay. So P equals nkt over v, that's the equation of state for an ideal gas. And now the second term, well, we get a minus sign, so this becomes positive kT times the derivative with respect to volume of this diagram sum. Okay. And now we are not going to add up all of these diagrams because there's an infinite number of them. And if I were cruel enough to assign you something like do the sum of the first 3 on a problem set, you would rapidly find that you did not want to do the fourth one. Okay? These diagram calculations, they get ugly very rapidly. But what we can say is we can go to whatever term we want. We'll just take the derivative with respect to volume of our diagram, and that gives us a new term in the expansion for pressure. Okay? And we'll focus on just the dumbbell diagram because that's sort of the leading order correction. That should be, if we've organized a good perturbation expansion, this should be the most important bit. Okay. Now, the perturbation expansion that we're going to connect these to is something called the virial expansion. Okay, I mentioned that at the top. The virial expansion is, or at least it was the title of this section. So we got to it. The virial expansion you might have seen in 358, but it's certainly worth bringing it back up. Essentially, this is an expansion in low density. Okay. So we say at low densities, our equation of state will look kind of like the ideal gas one, right? This is the ideal gas equation of state, but with a bit of modification. And so it's the nkt over v times 1, that's our ideal gas part, plus some coefficient times the density, and this is the number density, plus something that goes like density squared, plus, and on, so density cubed density. So we're expanding in low density. And now you should hopefully be starting to develop this sense, but let's say it very explicitly. Anytime someone tells you the density is low, density is a quantity that has dimensions. So if somebody tells you the density is low, your immediate response would be low compared to what? Good question. Question that is not properly answered when you just write the expansion like this. Okay. So what we're really going to be expanding in at the end of the day is this coefficient will look like a volume. And the density, you can also think of it as 1 over the volume per particle. So these virial coefficients, that's the name for the B, the C. If we went further, there'd be a D. Okay. The name for these virial coefficients, or rather, when you calculate the virial coefficients, their name is virial coefficient. When you calculate them, they will have a characteristic volume to them. And that volume will have something to do with the range of the interaction that we're looking at. Okay. So if it's an interaction with a range this big, then B of t is going to look, roughly speaking, like that distance cubed. It's going to be a volume that's connected to the range of the interaction. So you can also think of this as an expansion in the volume associated with our interaction divided by the volume per particle. Now, that's a good expansion parameter because it has no dimensions. You can actually say, is this big or small, right? So again, volume corresponding to the interaction length scale times the density is the same as divided by the volume per particle. Okay. So really the virial expansion, this is an expansion that asks, are we at low enough density that the interaction volume is much smaller than the volume per particle, which is to say the particles spend most of their time not interacting, right? They're zipping around through, they're sweeping out this sort of, I've got my volume, you've got your volume. The likelihood that we're close enough together to be within the interaction volume, which is much smaller, is low. Okay? And so you can see that turns out to be something that you could describe as an expansion at low density. Okay? And that is how people will describe the virial expansion to you. I think it's nicer to think of it as an expansion in interaction volume divided by volume per particle. And so this C of t, you can immediately know this is going to look like, because it's the next order, it's going to look like that interaction volume squared divided by the volume per particle squared. Okay. So this is how this expansion is organized. And I wrote this down here just because this is not necessarily how things are usually called in the perturbation expansion. The 1 is called the first virial coefficient. The B of t is called the second virial coefficient. Okay. So it's the first order in density, or maybe it's not because there's a density out front. But the way we've written it, you might be surprised that B of t is called the second virial coefficient. Now what we're going to do in the next section is actually calculate the second virial coefficient. Almost. So now we want to calculate the second virial coefficient, okay, which amounts to calculating this dumbbell diagram. Okay. And now, if you think back to our discussion from last lecture, we know the way to write this down. It's for 2 points, we're going to have n times n minus 1 out front over v squared. We've got a symmetry factor here, just a single reflection symmetry, or equivalently a single rotation symmetry. For this guy, you could describe it either way. So that gives us a symmetry factor of 2, so there's a 1/2 out front. And then the integral dr1 dr2 of f(1,2). Now, the Meyer function, or the f function, which is easier to remember than Meyer's name, but, is this e to the minus beta u, all of that minus 1, right? We're not going to put a value into that. So essentially what we're going to do is we're going to set this integral up, and then we have to stop because you have to specify an interaction potential before you can actually do the integral. Okay, and now since n is going to be a very large number, we can say, hey, n minus 1, it's all the same. So we can just call this n squared over v squared. And now you can see the connection to the virial expansion because, you know, we've got a power of density out front. If we did a diagram with 3 dots, we'd have 3 powers of density out front, right? So this is how the diagrams sort of directly correspond to the virial expansion. When you get to 4 dots, you'd have multiple diagrams, but okay, you get the idea. Now, in the homework, I had originally asked you to do a change of variables to R1 plus R2 and R1 minus R2. The key thing is that this Meyer function is going to only depend on the difference between R1 and R2. Yeah. Now, you can imagine some interaction potentials that would be more complicated than that, but most of the real potentials we're interested in are going to depend on the difference. So we'll assume that this is the case. And I left a 2 out of here. Got a little ahead of myself. R1, R2. Oh, that's awful. Well, you know it's a 2. All right, let's try that one more time. Much better. Okay, good. dr1, dr2. Now we're going to get rid of R2. So I jumped the gun a little bit here, maybe. We're going to assume that R1 and R... Oh, wait. Oh, no. I actually wrote the change of variables out here for you. Fine. Well, we're going to do this change of variables. To R equals R2 minus R1. And if you are sort of careful about this, you'll see that the Jacobian for this is 1. So the measure doesn't change when you make this change of variables. So down here we're going to have R1 and R, which is just R2 minus R1. And we're going to make this assumption. It's an important assumption, and I want you to think about it because it connects directly to something that you were asked in problem set 9. The assumption is that R1 and R can be treated as independent, right? R clearly contains R1, but we're going to assume that these 2 variables can be treated as independent. And again, think about why, because this comes up on the homework. And part of this assumption will allow us to say that R, the difference between the 2, has no volume dependence, and so f of R has no volume dependence, right? Because to find the pressure, we actually need to take the volume integral of the dumbbell diagram. So this is important to know, that this thing has no volume dependence, which means this function of R has no volume dependence. Okay, and that, again, connects to this assumption that R1 and little r are independent. So we've got our dumbbell diagram. We now change variables to little r and R1. And if they're independent, then we can reorder these integrals. When we do the integral over R1, this is just like all the other integrals that we've implicitly done to cancel off n minus 2 copies of v, right? The integral over R3, R4, R5, all the way out to Rn, each of those just gives us the volume of the box, okay? So now we've got an integral d3 of R1. This integral also just gives us a volume, which cancels one of these, and we come down to here. Now, this lack of volume dependence is important because that means this integral will not be affected by the derivative with respect to v, right? This is a constant with respect to v. So now we've got things set up so that we can take our derivative, right? So if we come back up to the virial expansion, we'll see we need kt times the derivative of the dumbbell. Okay. So kt times the derivative of the dumbbell, we see the form of the dumbbell diagram. 1 over v, so we take its derivative, we get a minus 1 over v squared. Catch a minus sign, there's that kt that we brought over, the half n squared over v squared, and the integral of this thing. And now if you, again, we'll look back up here, the virial expansion, we pull nkt over v out of the equation of state. So that's the ideal gas part, so just pull it over. Everything else is how you modify the ideal gas equation of state. And so b of t is nkt over v, n over v, the bt is what's left, right? So we've got nkt over v, the n over v is squared, so we've got an extra nv. That means we've got our virial coefficient isolated. It's this 1/2. Oh, I dropped a minus sign. Gotta be careful of those minus signs. Oh, and OneNote does not like me putting my hand on the screen to steady myself. Okay. So b of t is a minus 1/2 times this integral, right? The minus 1/2 and the integral are the only things we haven't written out explicitly to get it into the form of the virial expansion. And so here we go. And the last thing I'll say, this is good enough for our purposes, but I do just want to remind you again, this Meyer f function is e to the minus beta u of r minus 1. And we put things into this form precisely because this thing will be small over most of space. And the part of space that this is not small over is going to be defined in terms of this interaction potential. So this gives us a length scale, which we're going to integrate d3r, so it's going to end up giving us a volume over which this expression is not small, or rather is non-zero. Everywhere else, this will be very small. Okay, this is all we can do until we actually define u of r, and that's what we'll do in the last section. We'll define a particular u of r, but if you've been paying attention, you know, calculating this diagram is very similar to what you're doing on the homework when you're looking at a two-particle system. It's just that for a two-particle system, this is the whole story, whereas for an n-particle system, this is just the first approximation. So hopefully some of what we're doing here can help you out with the homework a bit. On the homework, I gave you a particular u, this hard sphere potential, which actually conveys a lot of information about how this expansion works, and that's why I wanted you to work through it yourself to get a feel for it. Is it the most realistic potential? No. The fact that you can do it analytically, though, means that you can start drawing more information out of it. And that's sort of, you know, many times for understanding the real world, what we want to do is have an analytic model, because then we can sort of play with all of the knobs and see how it changes, and a numerical model so that we can try to match to data. For matching to data, Schroeder focuses on the Lennard-Jones potential, and there it is, the Lennard-Jones potential. And it's an important potential, like historically and even in modern research. So I just wanted to give you a quick rundown on it. This is the form. So it's got, you know, something out front that sets the scale of the depth for the potential well. So this is the shape of the Lennard-Jones potential as drawn by someone who's not a very good artist. But the key features, it's got a potential well, it's got a non-zero radius where it reaches its minimum. It comes up very sharply at short range and rolls up towards zero much more gradually as you go to long range. Okay. So this coefficient U naught out front sets the depth of the well. R0 is the position of the minimum, of the bottom of the potential well. And then the form is 1 over r to the 12th minus 1 over r to the 6th. And there's a 2 to make things work out right. But the key thing is 1 over r to the 12 minus 1 over r to the 6th. This part is actually very physically motivated. It turns out that between atoms or molecules, if you're out at long enough range, the dominant interaction looks like 1 over r to the 6th. And I would love to spend the next half hour talking about the atomic physics and molecular physics that underlies that, but I won't do that. I'll just say, yes, this is actually what most atoms and molecules do when you're at sufficiently long range. Okay. So, and by sufficiently long range, I mean really just that there's no overlap between the electron clouds. Okay. So if these are my two atoms and my fingers are giving you sort of the extent of their electron clouds, at this distance, they're interacting 1 over r to the 6th, 1 over r to the 6th, okay, about here. Now you really start to have the electron clouds pushing against each other. Things get more complicated. But for long range, this is about right. 1 over r to the 12th, it's kind of physically motivated. The idea is just it's faster than 1 over r to the 6th, so after you make a potential well, you shoot up. Okay. But the 1 over r to the 6th is really only valid, to here-ish maybe. And the 1 over r to the 12 is really just there to give you a sharp increase as you go towards zero so that the molecules don't actually get to zero distance. And actually, it's a bit funny. Historically, this is what people wanted physically. And they said, well, we need something that shoots up at short range. Hey, r to the 12th is easy to calculate because if I've done this already, I just square it to get this. So it's actually, as much as anything, this is here because it's computationally easy. If you made this to the 10th or the 14th, the physics is going to work more or less the same. Okay, but so you can fit U naught and R naught for any given gas. And just to show you that this virial expansion really does work, this is data on, taken from pressure measurements. The virial coefficient over this R naught cubed, because remember, virial coefficient is some kind of volume related to the interaction scale. And then we're plotting it versus KT over U naught, which is to say, how does our temperature compare to the depth of this well? And as the temperature gets higher, we'd expect this to work better because at low enough temperatures, we're going to start to see some deviations, both because the atom spends a longer time down in this well. And if it spends a longer time down in this well, it's going to notice that this thing stopped being the right, description out here or so. But for temperatures that are above U naught, so here's where temperature equals U naught. If I go out to just double that, all of a sudden this data lies exactly on the curve that you would predict from the virial expansion. Okay? So we're looking at helium, neon, argon, hydrogen, all the way up to methane. So some very different kinds of gases. And again, you can see once you go below a temperature that's 2 times U naught, you start to get some scatter around. This is still kind of qualitatively getting the right behavior, but there's some scatter around it. But once you get up to twice U naught, man, this data just really follows that curve precisely. So this is showing you that calculating the first virial coefficient is actually capturing quite a lot of the physics that interactions bring to the table, right? So helium, neon, argon, these are noble gases. They maybe don't interact super strongly, but like carbon dioxide, methane, these have substantial interactions. And the virial expansion is really, really hitting the behavior correctly. Okay, so that's the end of our discussion of diagrams. In the next lecture, we're going to talk about a different interacting system, which is an interacting system of spins. So very different type of physical system, and we'll learn some new techniques for dealing with interactions over there.